Well, let's talk about Econ 382. All right, so game theory. John Nash, right? He was a guy that said,
Mathematician.
yeah, he was a mathematician. He said Adam Smith needs some revision. All right, he was like, this perfect competition stuff, it's just not right all the time. Okay, so let's talk about what happens when it's not actually doing what's in your own best interests that is going to be best for everyone, but doing what's in your own best interests and the best interests of the group. And he talked about what happens when you find out your best response to what other people do. So we're going to talk about that in terms of what we call game theory. How's that? Is that invisible? Yeah, oh, yeah. That's perfect. That's perfect. Here's a game, okay? This is a normal form game. You got player A on the left, that's standard, player B on the top, and A has a couple choices, and B has a couple choices, and we got some, let's do some payoffs right here. Yeah, let's do something like that, okay? So, this is a game written in normal form. Okay, so A, as you can see, can do one of two things. A can either whip or nay-nay, and player B can either whip or nay-nay with hand up. Okay, and they have different payoffs, with A's payoffs being on the left here and B's payoffs being on the right. You can also write this game in extensive form with, let's say player A is over here.
How do you do extensive form? Like, I always get confused when I try to set one up.
Well, here it is. We got player A can whip or nay-nay.
Oh,
and then you got player B. And player B can, in either situation,
right.
Player B, oh, we're getting some more people. Wow, look at this. Okay, player B can also whip or nay-nay as well. Okay, I didn't write this like super well. That's okay. And then you get these payoffs, right? So if both of them whip, we got 4-3. If A whips and B nay-nays, we got 1-2. Yeah. And then 5-1, and then 3-5. Okay? So it's going to look like this. And I would, if it was a simultaneous game, I'd put a circle around B to say that B does not know what node it's at. Okay? So that would be a simultaneous game. If I did not put a circle, that would be a sequential game, meaning A would move first, and then B would move after observing what A does.
Yeah, I guess my question is, how do you write the sequential form version of it? You know how you have like 8 boxes?
Yeah, this is an extensive form game, simultaneous. This is an extensive form game, sequential.
Okay, but like the one with the 8 boxes.
Oh yeah, you could do that if you wanted to as well. I would never see a point in doing that.
Including a test?
Personally, yeah, I see no situation in which this would not be sufficient.
Okay.
Yeah. Basically, you're just trying to write this, but in box form. And I just think it's awkward, so I was not going to do it.
So, like on a test, we can just write it like that and it'll be chill.
So, player A, right? Let's look at A's perspective, the best response. All right, if B whips, then A will want to whip. Okay? If B nay-nays, then A will want to nay-nay. All right? Okay, chill. Now, from B's perspective, if A whips, then B will want to whip. And if A nay-nays, then B will want to nay-nay. Yeah?
Taking it.
Uh-huh. Therefore, the Nash equilibrium is going to be right here. They will both end up nay-nay-ing. Correct? All right. Perfect.
How did you draw that with the arrows? What is the...
By the end of the week.
I just chose the box that has 2 arrows going into it. You could do it with check marks or stars too. Circles, if you've seen people do with circles, any way is sufficient. Okay, but this is the Nash equilibrium. Notice that that's the Nash equilibrium for the simultaneous game. In this particular situation, we'll do some backwards induction with our extensive form game. Our extensive form sequential game, and say, okay, let's look at B. Well, in this situation where A whips, right, then B is definitely going to want to whip, all right? But if A is nay-naying, then B is definitely going to want to nay-nay, all right? Perfect. Now, if A wants to maximize its payoff, knowing what B is going to do, actually, A is not going to want to get 3, A is going to want to get 4. So in this case, the subgame perfect Nash equilibrium is going to be they both whip in the sequential game. So notice in this case, the sequential game subgame perfect Nash equilibrium is actually different than the Nash equilibrium in the case of a simultaneous game.
So the reason why we do the extensive form is so we can say, out of these options, which is the best one for me to pick? Given that I know that these are the only options B is going to pick, I, as A, are going to choose this, so we end up in this version.
Yep, exactly. You know that these are not credible decisions that B would make, and so is A. By backwards induction, you're going to pick something else. That's how you get a subgame perfect Nash equilibrium. All right. So, all right. So that's good. That's good. Let's all right. Let's play a different form of this game. Let's change these payoffs a little bit. Let's say that instead the payoffs looked something like this. Yeah, something like this. Okay. So let's see what would happen in this case. So we got, from the perspective of A, if B whips, then A is going to want to whip. If B nay-nays, A is going to want to nay-nay. From the perspective of B, if A whips, then B is going to want to nay-nay. And if A nay-nays, B's going to want to whip. And okay, so in this case, we get this windmill sort of fashion right here. Okay, so we actually don't have a Nash equilibrium because they are always going to want to deviate. There is no point in which one player does not want to deviate to another strategy or another option. All right. So in this case, what we actually have is a mixed strategy Nash equilibrium. You cannot tell whether I'm going to whip or nay-nay unless you watch me. Okay. But since you cannot watch me whip or watch me nay-nay, we'll have to do a probability-based whip nay-nay comparison. So we'll do this by examining, okay, just by the way, I graded this homework recently, all right, homework 5. And I don't know how Dr. Lewis taught this, but I'm pretty sure, if I had to guess, that he did not teach it the way that everyone did it on the homework. Everyone was pulling out these P's and Q's that came from nowhere. But I know where they came from. I know exactly why everyone used the letters P and Q, and it's not because Dr. Lewis used the letters P and Q, okay? So, I'm just saying. Anyway, so,
I don't think I use pi.
Here's how you solve a mixed strategy. There's actually a couple different ways.
That's crazy.
In a simple scenario, which I'm not going to show, but this is what most people did, and this is what chat did, is that you take the expected, so what you want to do with your mixed strategy is you want to play so that the other person is indifferent in what they decide, okay? So the way that chat did this, the simple way, is they take your expected payoff from one strategy and your expected payoff from another strategy, and you set them equal to each other. We're going to do it in a more generalized way that actually gets you the same answer, and it's not more complicated. But that's the idea, is that let's take the perspective of B. Okay, from the perspective of B, I want to play my strategy in such a way that A is indifferent between whether to whip or to nay-nay, okay? So that means that as B, I'm going to make my choice by looking at the expected utility of A. Okay? And the expected utility of A is going to be, or the expected payoff of A, I'll call it utility, but this is the expected payoff of A, okay? So there's some probability, we'll put some probabilities over here. We'll say the probability that A whips, and we'll do the probability that B whips, okay? And then obviously the probability they nay-nay is going to be 1 minus that. All right? Cool. All right, so the expected payoff of A is going to be 2 in this case. So 2 times the probability that they both whip, okay? plus 0 times probability that A whips and B nay-nays, minus B whip, okay, plus 0 times probability that B whips and A nay-nays, okay, plus 1 in the case that A both nay. Okay, so this is the total expected payoff of A. I've put every single situation in terms of probabilities, all right? Obviously, these zeros are going to cancel out, and you're going to end up with something like 2 probability A whip, B whip, plus, what is that, 1 minus probability B whip minus probability A whip minus, oh, that's going to be a plus probability that they both would. I'm actually going to move that term over here and just make this a 3. Okay, so there you go. And to make A indifferent, okay, so this is the expected payoff of A. Now, looking in terms of what would make A indifferent, I'm going to take the first order condition, meaning I'm going to take the point at which A going one direction or going another direction, A is indifferent. It's like the maximum of their expected payoff curve, okay? So I'm just gonna take the derivative, the expected utility of A, with regards to A's choice, or A's probability of whether they're going to whip, okay? Again, let me back up. I am player B. I'm going to choose my strategy based on what will make player A indifferent. So I'm solving for what will make player A indifferent right here, okay? I'm taking the first order condition of their expected payoff. And then I will find out my strategy as player B. Yeah? Okay, let's do it. So it's going to be, with respect to A whipping, it's going to be 3 probability B whip. The 1's going to drop out. Minus 1, first order condition, that's going to equal 0. Therefore, the probability that B whips is 1/3. In other words, as player B, I'm going to play a 1/3 probability of whipping. That's going to be my strategy to make A indifferent. Okay, so that is how that goes. All right, and then for the same kind of thing from the perspective of player A, I am going to play the strategy that makes B indifferent. Okay, so I'm going to take the expected payoff of player B, which is going to be, then I'm going to take B's payoff. 0, in this case, right, plus 1 with probability of A whipping and B nay-naying, right? I'm going to write this out. Plus 1 times the probability that B whips and A nay-nays. I'm writing that right? Yeah, and then 0 in the other case, okay? And then I'm going to do the same thing. I'm going to solve for what makes B indifferent. And I'm just going to skip this part here, but A is going to play a strategy where its probability of whipping is going to be 1/2. Okay, so A is going to play a 1/2 probability strategy to make B indifferent. Okay, so your Nash equilibrium is that A whips with the probability of 1/2 and B whips with the probability of 1/3. Okay. Questions on mixed strategies? Or does the squinting mean that everything makes sense?
She's blind. Can't see through.
Okay, so again, in theory, you could, this is what chat did. You could take the expected utility of A in the case where A whips. I don't even know how to write that, but and then that would be, you'd basically separate this probability in half, right? And then you get the expected utility of A in the case where A nays.
Then you set them equal to each other.
Then you would set them equal to each other, and you would get the same answer. Should get the same answer.
And in that case, you don't even involve the probabilities of the other one. Or do you?
Yeah. So in these simple games, you should still end up with this right here. But in these simple games, you should be able to do both, and it should solve the same way. This is how I prefer to do it because that's the way it was taught. But
I've got a question, Stephen.
yeah.
When we're taking like a first order condition, what are we taking in respect to?
So
For the first one, yeah.
Yeah.
I just can't see it.
Oh, so you're taking the
Expected utility
derivative
of
of
A.
A's
with
expected
I.
payoff with respect to A's probability of whipping. Yeah.
In other words, we're using backwards induction.
Yeah. I think. Let's just say yeah. Sounds right. Okay. If there are no more questions on mixed strategy, I'm going to move on to something else. But I want to make sure everyone understands mixed strategy. Equilibriums.
So when there's a mixed strategy equilibrium and we don't have an equilibrium like that, we have to use some kind of probability to be able to determine what our best pick is to be indifferent.
Yes.
And that's what these pi represent. They represent the indifference.
Yeah. Yeah. So this is just the probability that each one chooses a certain strategy. We solve for what makes the other player indifferent, and they both do that, and that's the equilibrium. Okay. If you get a question like this on the test, and it says solve for the Nash equilibrium, and you say there is no Nash equilibrium, you will get that question wrong. Okay.
Understood.
All right. Here's the payoffs again. We like changing payoffs and playing games. So let's continue to play games. Okay, so consider a situation like this. Let's see. What kind of game is this?
Is this a prisoner's dilemma?
It is, yes. This is a prisoner's dilemma game. All right, so you'll notice that the socially optimal point is for the Pareto efficient point. Well, I guess there's multiple Pareto efficient points. We'll talk about that. So the socially optimal point is that both of them will choose 3-3. But that's not a Nash equilibrium because they both have incentive to deviate from that 3-3. So they'll both deviate, and then at this point, each of them would deviate as well, so we'll end up at the 1-1. Okay, so that's classic prisoner's dilemma. So you can see at this point, 3-3, this is Pareto efficient, okay? You can't make one person better off without making the other person worse off. So that's Pareto efficient. Is this point Pareto efficient right here? 0-4?
I don't think so, no.
Definition of Pareto efficient, you can't make one person better off without making someone else worse off. So actually 0 is Pareto efficient because the only way you can make someone better off is by making player B worse off. So these three are Pareto efficient, but the 1-1, you can actually make them both better off by going to the 3-3. All right, if you could mandate the outcome. So you have 3 Pareto efficient outcomes here, but you do have that 1-1 where they end up, which is
So
actually
1-1 is not good.
yeah, it's the only non-Pareto efficient outcome. Not that these are good necessarily, right? Socially optimal would be at 3-3, but your Nash equilibrium is 1-1. So that's what a prisoner's dilemma looks like. And okay, so in this game, right? Let's say, okay, they want to collaborate, okay? And let's say that they play this game for 10 time periods. And for 10 time periods, they're going to say, hey, let's both just whip. All right, it's better for both of us. Is that going to work out?
No,
No, because, well, what if they play for 100 time periods?
definitely not.
No, because by game theory, they're going to say, well, you're going to deviate in the last time period, therefore you're going to deviate in the 99th time period, therefore you're going to deviate in the 98th time period, and they just go back and back and back, and they're like, well, we'll just both deviate in the first time period. So it's just not going to work. Okay? So that's why a finitely repeated game, they are not going to be able to sustain collusion. But if it's infinitely repeated, then you have a chance of it working out, right? Depending on how much you value the future. So in an infinite time period, then let's say, all right, let's just do from the perspective of, well, they're symmetric, so it doesn't really matter. So your payoff, and in this case, just to be confusing, I'll use pi as payoff. So the payoff from, all right, let's define some things. So let's make pi, I don't know, C, the payoff from colluding, yeah? Collude. We'll make pi D, the payoff from defecting. We'll make pi, let's see, I don't know, what's a situation where what's the other one? Oh, Cornell. Well, that also starts with a C. Let's do an N. Nash. All right, that's the Nash payoff. Call that Cornell. Okay, so those are all your payoffs. So we will say that the payoff, in the case where they collude, right? We're going to compare this, and we're going to compare the payoff in the event where they defect. Okay, so if they collude, here's the payoff for each of them. So in each period, it's going to be 3 plus 3 times delta, which is how much they value the next time period. Okay, plus 3 delta squared plus blah 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 all the way to infinity. Okay, so this is a geometric series, and a geometric series from 0 to infinity of a r to the I won't use r, I'll use delta. A delta to the n is going to be is going to be a over 1 minus delta. Okay, so that's how a geometric series works. Okay, so in this case, we're going to get a payoff in the case of collusion of 3 over 1 minus delta. Okay, in the case where
Steven,
yes,
can you write on this side just because the monitors are blocking the...
are they for real? How's that? Does that fix things?
One more row and it's gonna be gone. But
Okay.
I just picked a poor spot.
You might be able to rotate it a full 360 degrees.
Like, is this one blocking you? That's the one blocking you? This one is blocking you.
Yeah.
Yeah, like that.
Yeah, sure.
All right.
Thank you, Steven. That works good.
That's what we call a cooperative strategy.
If you defect, your payoff in the first time period is going to be 4. And then your payoff is going to be the Nash forever. So you're going to get 1 delta plus 1 delta squared all the way to infinity, right? So because I want this to start at 0, this is actually pretty important, okay? So I'm just going to change this into, I'm going to split this 4 up and make it 3 plus 1 delta plus 1 delta squared all the way to infinity, okay? Because I want that first term there. So now I can converge this geometric series right here and get 3 plus 1 over 1 minus delta. Okay, that's where I defect, okay?
Sounds good.
So, so I'm going to solve for what delta needs to be in order for collusion to be sustained long term. So that means that 3 plus 1 over 1 minus delta is going to be equal to 3 over 1 minus delta. So in other words, 3 is equal to 2 over 1 minus delta, and what is that? 3 minus 3 delta equals 2, so
Wait, where did the 2 come from?
I just subtracted 1 from 3. Yeah. So then 3 delta equals 3 halves? Yeah, okay. So delta equals a half. what I got the first time. 3 plus 1 minus delta. Okay, 3 equals 2 over 1 minus delta. 3 minus 3 delta equals 2. And what's going on? 3 delta equals 1. Delta equals a third. There we go. All right, so in this case, if delta, that's how much you value the future. This is your discount factor.
Steven, what did you just do?
In terms of algebra or in terms of concept?
Concept.
Okay.
Did you set two of them equal to each other or something, or?
Yeah, so your payoff in the event where you collude, let me write this out. So
I get what that is.
so for
They
this
got the payoff of the collusion.
has to be greater than or equal to your payoff for defecting. Okay, so you're going to solve for delta in this case. So actually, I probably should have made this a less than or equal to. And then this would be a less than or equal to, and this would be less than or equal to, and then you'd get delta is greater than or equal to 1/3. Okay, so yeah, that's how that would work.
Sweet, thank you.
So you have to value the future at least 1/3 in order for collusion to be sustainable in this scenario. Okay? So again, delta is your discount factor. Do not call delta the discount rate. You will regret that later in the class. Do that. Okay? Perfect. Okay, any questions about infinite games? Now, just as another way that you could solve this, because this is a simple game, you can actually solve this just by looking at the first time period. So if I look at the first time period, then my delta would have to be greater than or equal to my the increase in payoff I get from defecting relative to the difference in payoff from colluding. Wait. Colluding minus. Does this make sense? Okay, this is the difference in. This is what I get over. Yeah, because that's Cornell, right? So, oh yeah. This is going to be Nash, right? Cornell needs to give me some payoff over. No. I'll write the first time. Yeah. Okay. Let's just see if this works out, okay? Because in my mind, yeah, the difference in payoff from defecting over Cornell needs to be the ratio between that and the payoff from colluding over Cornell. That has to be like significant. Let's see if this works, right? We're just gonna look at the first time period. So this would mean that delta is greater than or equal to, and defecting would be 4. Cornell is 1. Colluding gives you 3. And Cornell is 1. So what is that? That gives you 3 halves. No, that doesn't sound right at all. Yeah, I must have. Wait, no. Okay, yeah. Let's just change these around. I got confused with how I was defining my variables. Okay, so the C, colluding, that's going to be 3, yeah? Okay, and then colluding and Nash, which would be, no, we'll do Nash and colluding. That would be 1 minus 3 equals 1. Wait a second. I swear I wrote this down somewhere.
What are we trying to say here?
Some random shortcut. It's actually pretty dope.
Oh.
I've seen it before. I don't remember what it was though.
What was this on, 7? Oh, it's sick. Okay.
One again.
But then that just means you. All right.
I don't know how you can get through in the bottom because you'd have to get doing
no,
0.
that's right.
Yeah.
Right? Oh no, I lost it.
Oh yeah.
Wait, no, that's
Yeah.
Anyway, there you go.
Should be
So what is this again?
So again, you can theoretically get the same answer if you trust this process of setting the ratio, delta greater than or equal to the ratio of just looking in your first period, your payoff from defecting minus your payoff from Nash or Cornell over your payoff from defecting minus your payoff from colluding. Wait, I said that backwards.
well, what's in the denominator there? It's kind of hard to read the subscript. Is it D or
That's a C.
the other one?
It's
It's
defecting.
Oh,
Yeah, it's a D.
Yeah.
So this minus this over this minus this. You guys get what I'm saying?
Yep.
Okay. I think I changed that again. Yeah, that should be it. That was way more simple the first time I did it. Sorry about that. Just do this if you're unsure. This will get you there. Okay. Any questions on infinitely repeated games, the delta geometric series process?
In a question, when he'll like be asking that on an exam, will he be like, "What is the discount factor?" And
Yeah, I can see
will
that.
he specify that it is an infinite game?
Yeah, it would be obvious that it's an infinite game, or like even if he asked what's the discount factor that would be necessary to sustain collusion, that would imply that it's an infinite game.
Okay.
So, yeah, good question. Any other questions? Okay. In that case, let's move to a different topic. All right, we've been talking about games and game theory and whipping and naming for long enough. Okay, let's do some. Let's talk about some terms that don't fit into perfect competition. Okay, so we have a monopoly. All right, that's the case where number of firms equals 1. All right. Hopefully we are not lost yet. Okay.
Can you explain monopoly for me? I'm joking.
Then we have a cartel, okay? A cartel is like a big monopoly. Say we equals 1. All right? Because we're just one big happy thing, okay? You just put yourselves all together and treat yourselves like you're a monopoly, okay? That's what a cartel is. Corno. Corno is where you have firms that compete on quantity. Okay? And actually, let me make it specified, they do that simultaneously. Okay? That is what Corno is. Stackelberg. Stackelberg is where you have firms that compete on quantity, but they do it sequentially. All right, so there is a first mover and a second mover. And the first mover in Stackelberg typically has an advantage because they get to choose their quantity and release it out into the market. And then the second person just kind of has to deal with that and respond in turn, okay? So that's Stackelberg and Cornell. Bertrand. It's actually pronounced Bertrand, in case you were wondering. You don't have to put that on the test, that pronunciation. But this is where firms compete.
On our 388, we have to know how to say heteroskedasticity.
There you go.
So that's cool that we do.
So, well, maybe we should practice this. Okay, everybody. Econ. Oh, there we go. There we go. Nice. Nice. Okay, you're ready for the exam. Cool. Okay, this is where firms compete on price. Okay, and there's actually two different kinds of Bertrand. Okay, there's differentiated and undifferentiated. So, in undifferentiated Bertrand, okay, what happens is that you have your price that's going to be more than your marginal cost, and nope, it's wrong. It's wrong. This one. It's wrong. Okay. In undifferentiated Bertrand, what's going to happen is that your companies, because they have undifferentiated products, are going to compete in a price war, and they're just going to go further and further and further down until price is equal to marginal cost. Okay, so that is what's going to happen in undifferentiated Bertrand. Okay. In differentiated Bertrand, it's a little bit different. In that scenario, because you have differentiated products, you're actually still going to get profit. Your price is going to be more than your marginal cost, and you will have positive profits. Okay? Even though you're competing on price, you have enough differentiation for that to happen. Okay? So Bertrand is actually different from monopolistic competition. In monopolistic competition, you similarly have all of these. They're not monopolies because there's more than one firm, but they are competing. And in the long run, for monopolistic competition, you will get prices more than marginal cost because they do have some market power. But in this case, their profits will actually go to zero. Okay, so that's what makes monopolistic competition different from differentiated Bertrand. So those are some.
Is that the one where we're figuring out how many firms have to enter profits to go zero?
Yeah, and this is specifically a long run condition because they can't have positive profits in the short run. But yeah, okay. So you got that. These are all general definitions of these things. In terms of monopoly, some notes on monopoly. Okay, so some of this is 380 review, but monopolies. There are different kinds of price discrimination that you can be aware of in monopolies. So we draw some ISLM model for you guys. Yeah. Okay. So you got your monopoly. You got a demand curve. You got a marginal revenue curve, and you got a marginal cost curve for your monopoly. Okay. So in perfect price discrimination, you are going to charge everyone their willingness to pay. So you're going to capture all of the surplus. It's all going to be a producer surplus. That's what perfect price discrimination is. That's first degree. In second degree price discrimination, you are going to discriminate based on the different quantities that consumers buy. So you'll choose different segments. Let's say you have a segment for this quantity, and you have a segment for this quantity. Okay? And you are going to capture each of those segments individually.
So the first one is perfect price discrimination, or what is it? Or is it just?
Yep, first degree price discrimination or perfect price discrimination is what you call this one. Discriminating based on quantity would be second degree price discrimination.
Is second degree like electricity companies?
Yeah, I would say, well, we might come back to that one because probably what you're thinking of, I would say in most situations that would probably be the fourth one we're going to talk about. So let me come back to that. But perfect price discrimination, or second degree price discrimination, I can't think of a good example of that right now.
Student discount versus normal discount.
So that would be like third degree price discrimination. See, we don't talk about second degree. Third degree price discrimination would be where you have where you price discriminate based on characteristics of consumers. So like senior discounts or student discounts, right? You have two different groups of consumers with different characteristics, And so you're actually going to have, you're going to separate them into different demand curves. And you're going to choose a price that you charge this segment, and you're going to choose a price that you charge this segment. Okay, so between these two, that's third degree price discrimination. You're separating consumers by characteristics, like seniors or students and the rest of people, and charging different prices. Okay?
So is second degree when you produce something the first time and then you produce it a second time at a different price?
Nope. No. That is a several time period
Oh.
monopoly.
Could second degree be like, if it was like business to business, there's like a bulk discount? Like if you're buying
Yeah,
a large
that's a great
quantity
example.
or something, but like,
So bulk discount. You buy a certain quantity, I give you a discount on that quantity. Yeah, that's second degree price discrimination. Okay. Another type of price discrimination is two-part tariff or two-part pricing. Anything that sounds relative to that right there. So essentially, you have this monopoly, and typically they're going to have a very low and flat marginal cost, something more like that. Okay, and in this type of price discrimination, what's going to happen is that they're going to charge some entry fee, and then after that, everything that someone buys, they're going to charge at marginal cost. The way this works is that their entry fee is going to be, see this consumer surplus right here? So they are going to take the area of that triangle, basically, whatever the total consumer surplus is, and this is going to be their entry fee.
Like Costco.
Like Costco. Yep, exactly. So to be clear, their entry fee is a total entry fee. So this might be $18,000, right? But they're not going to charge everyone $18,000. They're going to charge a total entry fee of $18,000. So if they have, if 1,000 consumers that they plan to buy their product, then they're going to charge each consumer $18. Make sense?
Is this like a club good then?
Yeah. So Costco, great example. They charge everyone an entry fee. So they collect. Notice they collect all the consumer surplus, and then they charge at marginal cost after that. So everyone buys a certain quantity, and it's just at their marginal cost. So in this situation and in this situation, notice that these are socially optimal, right? Socially optimal, Pareto efficient. They're capturing all the surplus. There is no dead weight lost in strategy 1 or strategy 2. But there is dead weight loss, as you can see here, in that strategy and in these strategies right here. That's all dead weight loss. Okay? So those are types of price discrimination. And so what you were talking about is electric companies will probably be more like, oh, by the way, when you're price discriminating in third degree, what makes this work, by the way, is the fact that your different consumers with different demand curves, they have different elasticities. They have different demand elasticities. So that is kind of the key concept behind third degree price discrimination. But what you were talking about with electric companies, that would probably be more like a natural monopoly. So a natural monopoly has a different cost structure where they have really high fixed costs, and their average cost curve and their marginal cost curve are going to look like that. Okay, and then they'll have some demand curve, I guess. Yeah, right? Okay, so we got average cost, marginal cost. And so basically their average cost curve is decreasing, okay? And their marginal cost curve. Their costs are decreasing the whole way through. Okay, this is what makes someone a natural monopoly. And in a natural monopoly, so one way that you might try to solve that problem with a natural monopoly is you'll be like, okay, let's charge a two-part tariff, okay? We'll capture this set of consumers, right? And then we'll charge marginal cost after that. Although I suppose you could also apply second degree price discrimination or even third degree price discrimination and charge someone a higher rate or charge someone, charge a different set of consumers a lower rate. But the fact is that, if you wanted to just set your price equal to marginal cost, then why would that not work?
Well, because you'd be making negative profit.
Right. They would lose money and they would go out of business. Okay? And in fact, even from a social planner perspective, it's inefficient to have more than one company in a natural monopoly setting because since you have constantly decreasing costs, if you had multiple companies, you'd be replicating your fixed costs, your really high fixed costs, and that's just not efficient. So it's actually most efficient to just have one company doing this, whether this is electricity or whether this is, water, sewage, other examples like that. So, so you could use two-tier pricing. You could put a price cap, maybe put the price cap at average cost. But then the problem with that is that they have no incentive to keep their costs low. So that also has its own problems. Another thing you can do.
Price floor?
Huh?
Price floor?
Price floor?
Oh, it's dead weight loss, but
Yeah, that's what I meant by a price cap.
Hmm.
Price cap, price floor,
Price
those are the same
ceiling.
thing.
quantity cap?
I just meant can't charge more than that.
Okay.
Yeah, that's what I meant. So another thing you could do is rate of return regulation, which a lot of the time is done by some ratio of profits to capital, right? So, hey, your profits over capital, those cannot be above, some certain number, okay? So that might work, but if you were a company and you were told, hey, your profit to capital ratio can't exceed a certain number, then what might you be incentivized to do?
Make your capital more expensive.
Yeah, just get solid gold and plate it onto your capital.
Oh, what is this called? Gold plating? or
Yeah,
something?
gold plating. So you just make your capital really expensive so that you stay within that rate of return regulation. So natural monopoly regulation, there's different strategies and they all have their own problems that you're dealing with that. Okay. Yeah, but that's how all those all go. Other models that we've talked about that are that don't fit into perfect competition. You guys talked about the hoteling model, right? This is where you have a line, and a lot of times it's just 0 to 1 to make it really simple, and you have some firms, say firm A and firm B, situated on this line, and this is really just a symbol of differentiation. So, in problems they'll use a beach example, oh, you guys are two shops on a beach. But it's more than just a literal example like that. It's the difference between an iPhone and an Android, right? That's not, so in that case, distance is the amount of differentiation between those two products. And really what the hoteling model is saying is let's make some assumptions. We'll say how much consumers value a product that's exactly what they want, and how much they dislike having a product different from that. That's what we call travel costs. So that's what travel costs are in this scenario. It's just I don't want differentiation. If travel costs are, in most of our examples we've talked about, companies are incentivized to just go right next to each other. Here's A, here's B, and they have minimum differentiation. They just choose the middle, and they let everyone come to them on either side. We're assuming that every customer buys in this scenario. There are a lot of simplistic assumptions, and you can change those, and a lot of stuff changes. If your travel costs, you have some factor of the distance, right? That's your travel cost. But as soon as you go, oh, it's some factor of the square of your distance, let's make travel costs quadratic. Well, then suddenly this problem becomes A goes all the way over here and B goes all the way over here. And now they want max differentiation just because you made people you made people, it'd be more expensive for people to have a product that's different than what they want, right? So, and in this case, they actually prefer that because they're not doing a price war like they would be doing if they were right next to each other, because they were undifferentiated. So, you guys don't need to know all that stuff. That's just like, I'm just telling you that because the hoteling model is just given to you as a concept to understand about differentiation, but it can represent a lot of different things, and it's not necessary for you to memorize all these formulas and assumptions for a hoteling model, because they change that all the time, anyway. And then the other way we modeled that is like a circle model. Say you have some firms A, B, C, that are all in this circle, and again, the strategy changes if you model it like this, because now your firms are going to want to space themselves out, again, assuming travel costs are linear, but B would not want to be here, right? Like, B is pretty squished between A and C, so we would probably move somewhere over here. So he would capture more of this market share over here because of more differentiation. Okay, so that's what we learned from the circle model. There are a few things from the circle model that that conceptually we like to know. For example, if you have higher fixed costs, then you'll have lower firms. That's intuitive, right? So more firms will exit the market if your fixed costs are higher. If you have higher travel costs, then you'll have more firms. Okay? Prices will fall as you have more firms. And then the other thing that might not be intuitive about this model is that when we solve for this model with the assumptions that we have in equilibrium, you actually get over-differentiated. You get too many firms that come in than you would plan as a social planner, because they're all replicating their fixed costs. And as a social planner, you would not replicate those fixed costs. You would consider it all as kind of just like one company. So you would have less firms. Kind of in the weeds, but that's the circle model right there. Again, conceptual stuff less than mathy stuff is what is the most important takeaway from the circle model.
Can you explain when you were talking about like how it gets over differentiated, like just what you said at the end? I just like didn't.
Yeah, so basically a takeaway from the circle model is you get if I was a social planner and I was planning for how many firms would be socially optimal for society, then I would plan a certain number. And like if I were doing the math, right, I would plan a certain number of firms. But what we find is that when we do the math in terms of what firms will choose, we find that there are more firms than is socially optimal. So the market is over-differentiated. There's more differentiation than is socially necessary.
Why? Why is that? Is that important or?
It's because as a social planner, I would take into account the fixed costs for society, and the firms are not doing that. They're just taking into account their own fixed costs. And so what you get is a lot of firms popping up, paying all of these fixed costs. And it's not necessary to replicate that over and over, but that's what they do because they're just focusing on themselves. Did I explain that very well? Does that work?
Yeah, I think that makes sense.
This is a good list of the kinds of models that we've gone over. This is the list of the models that we've gone over, and some of the different things that we find from them, the differences between them. In Cournot and in Stackelberg, you will find and in Bertrand, you will, Bertrand? Yeah, I think Bertrand too. You're gonna be finding best response functions to firms. So like in Cournot, I'm going to find a function basically maximizing my profit based on someone else's quantity, right? And it's and both firms are going to do that simultaneously. So you're going to get this response, this reaction function for both firms, both trying to maximize their profit. In Stackelberg, you're going to do the same thing, except one firm is going to choose a fixed quantity, and the second firm is going to have a reaction function to that firm's fixed quantity. Okay? And again, you're maximizing profit. So you maximize profit, but you assume that you get a fixed quantity from this firm, and you get a reaction function from that.
So then with Bertrand, what does your profit function look like? Is it in terms of P instead of Q?
Yeah, so you're going to be choosing, so in Cornelius Stackelberg, you will be choosing Q. But in Bertrand, you will be choosing P. You'll be choosing Q and reacting to Q. In Bertrand, you're choosing P and reacting to P.
So our equation will be P times whatever the Q in terms of P is, or something like that, in our profit function.
Yeah, you would put it in terms of price instead of in terms of...
You wouldn't use the inverse demand curve, we would use the actual demand.
Well, price equals something, that would be the inverse demand curve, yeah? So, yeah. But if it's undifferentiated Bertrand, just price equals marginal cost. Like, that's all you need. So, and your profits would be zero.
And your quantity might be zero also if it doesn't have a marginal cost. If it's only a fixed cost, then you'd say that your quantity is zero. Profit zero.
Not to my knowledge. I think they both would still produce a quantity. Whatever quantity where price would equal marginal cost. Okay, that is the material that we have covered in class so far. Now, okay, so I made a practice exam for this class that we can go over. Before doing that, do we have any questions generally on anything that we've talked about? No. Yes.
Have you seen the test?
I have.
You have?
Yes.
Listen to Steven.
So going back to the beginning here, when it comes to the the sequential games, and you have the 4 different L if S, S if L, L if L, L if S, and all of those kind of things. How do we write one of those, and how do we do the Nash equilibrium with one of those type of problems? Unless you're just going to say, don't worry about it.
If you were me, I would not. But if you really want to, so here's A. Nay, nay. All right, here's B. And nay, nay. Okay. Bad writing. Let's just say this is 3, 3, 2, 2, 1, 1, 0, 0, just for ease. Okay. So if I wanted to write this in normal form here, A would move first. So A can only do 2 things. Okay. So A's on the left here. All right, we're for nay, nay. All right. And you see for B, there are 4 different situations that can play out. Okay? So maybe that's not the best way to describe it. Sure. Okay. So B's strategies are, I'm going to whip if A whips, and I'm going to whip if A nay-nays. Essentially, I'm going to whip no matter what. Okay? Or you could say, I'm going to whip if A whips and nay-nay if A nay-nays. Or I could nay-nay if A whips and whip if A nay-nays. Or I could nay-nay no matter what. Okay? So in this situation, where B whips no matter what, you get nay whip, B whip, which gives you this one. Okay? If A nay-nays, well, B's going to whip no matter what, so you're going to get 1, 1. If A whips with this strategy, then B is going to whip. Okay? So we're going to get 3, 3. If A nay-nays with this strategy, B is going to nay-nay. So we're going to get 0, 0. See how we're solving that out? Yeah? So you basically just say, okay, this first one, is what if A whips. The second one is what if A names. That's what B is going to do. And then you're just going to take these numbers, and you will get duplicates here, just because of the nature of the game. That's how it's solved.
Then how do you do the check marks or the stars when you have 8 different boxes?
Yeah, again, I wouldn't. But basically, you would do it the exact same way that you would do a normal form game. So let's say,
A chooses whip.
so if A whips, E nays, you get 2, 2. If A whips and this is E, so that's another 2, 2. Okay, so if A nays, E whips, or no, 2, 2. That's it.
And 1 more.
No, A name is B whips. That's right. One more.
There. And then the other one's 0, 0.
And then this is so, yeah, in this situation, we would say, okay, if A whips, then what's B gonna do? Well, B's biggest payoffs are here and here. Okay? If A nays, what's B gonna do? B's biggest payoffs are here and here. Okay. Now, if B whips, or if B chooses this strategy, A's biggest payoff is here. If B chooses this strategy, A's payoff is here, then here, then here. So your Nash equilibria are going to be here and here.
So what you do is you go from the columns instead, is that what you do? You say B chooses this, then A should choose this. B chooses this, A should choose this.
Mhm.
You just do it from the columns.
Yeah. And the exact same way you solve a you're just doing columns this time. Okay. Sick. Any more questions, or do you guys want to go over practice test?
See you later, Sam. Thanks, Steven.
Steven. All right, let's do it. Let's see what we got here. Where is this? Okay. What if I can see my ass actually? Ah, here we go.
Look at all the cool tabs. 116, 114.
Steven, I'm sure he can like
Oh, like 70 tests. It's like yes. I'm just immediately like.
This is exciting.
Where'd you go making a whole test, dude?
I know.
That's fire.
You can donate to my Venmo to show appreciation.
You should throw this up
Do
on
you-
the Learning Suite.
Yeah.
Yes, I will send this out.
Do you have a Venmo? Would that help if we
His wage rate.
Okay, so true or false? A monopolist practicing third-degree price discrimination will charge a lower price in the market with the less elastic demand.
It's true, isn't it? Because it's less elastic, so it doesn't it's less resistant to change.
Would it be a higher price? Would it be false?
Yeah.
Because if it's less elastic, then they're
Oh,
going to
yeah, it
be
wants
more
to have a
willing to
higher
pay
price.
the higher price.
Yes.
The one that's more inelastic can have a higher
Exactly.
price.
Yeah, you can afford to charge them a higher price because what are they going to do, right? So that one's a true. True or false? In a core no duopoly, each firm's reaction curve.
Was that false or true?
The first one is true. Yeah.
Wait.
Or, sorry, false. False. Sorry, you guys were right. I was also right, but said the wrong thing. Okay, so in a Corno duopoly, each firm's reaction curve shows the profit maximizing price for that firm given the price set by the other firm.
Isn't it for quantity?
It's for quantity.
Exactly. Nice, okay. The prisoner's dilemma is a classic example of a game where the dominant strategy equilibrium is not Pareto efficient for the players.
That's true. It's true.
Yeah, that's just straight up true. Okay, true or false? If a firm's average total cost is decreasing for all relevant levels of output, the firm is a natural monopoly.
Wait, hold on.
It's true.
Isn't that
Yeah, that's just the definition of a natural monopoly. That's not tricky. True or false? In a sequential move duopoly, the leader, or the first mover, has an advantage because it can commit to an output level, forcing the follower to react to it. That is also true. Okay, for a single price monopolist, the marginal revenue curve is below the demand curve because the monopolist must lower the price on all preceding units to sell one additional unit.
Yeah, you have to.
true?
I think reduce the price so that one additional unit is sold.
That one's also straight up true.
True.
Yeah.
That's just like the definition.
A lot of these are just definitions, not trick questions. True or false? In a hotel linear city model of product differentiation, firms have an incentive to locate in the exact center back to back to minimize their average costs.
False.
False? Why false?
Does it affect where you are? Like,
They're not trying to minimize their average cost.
Yeah,
They're
they're
wanting
trying to increase their market share.
exactly. Yeah, they're profit maximizing. So not cost minimizing. But they will locate in the center. Just
But
not
not for that reason.
Not for that reason. True or false? A grim trigger strategy can be an effective way to maintain a cartel that is only anticipated to last a short while.
I don't know what a grim trigger is.
What a grim trigger.
Yeah, what is
What's
a
a grim
I was on the homework.
I know that
So-
we called it a trigger. I don't know if we would have called it a grim trigger.
Yeah, a grim trigger is just like, okay, look, we're gonna collude, or else. All right, basically, I'll collude if you collude, but as soon as you don't collude anymore, then I'm never gonna collude again.
So this is false.
False?
No, it's true.
Wait.
Because that's
You only-
intended to
it's-
last forever.
That is-
Or at least until somebody deviates.
Wait.
Well, it's not meant to last a short
Can
while.
be-
It's meant
No,
to
it's true
last-
because someone will defect. I mean, that's what we learn in the
Yeah.
in all of our
Wait,
game
can
theory
you
stuff.
Cartel doesn't only. Oh yeah.
Okay, well,
Yeah.
maybe the question.
So a grim trigger strategy could work for an infinite number of time periods, but not for a finite number of time periods.
Right.
So it is.
False.
That's false. Yep, exactly.
Yeah, it doesn't work for
Exactly. All right, true or false? A two-part tariff consisting of a per unit price equaling marginal cost and a fixed entry fee equal to the entire consumer surplus allows monopolists to achieve a Pareto efficient outcome while capturing all social surplus.
That's not a two-part. Yeah, that's a two-part tariff. Oh, wait, hold on. Yeah,
True.
by
Yeah.
definition.
Yeah, these are, yep, another one of those. Okay, true or false? In Bertrand oligopoly, firms with similar products compete on quantity with simultaneous choices.
Isn't it?
No, they compete on price.
Exactly, yep. Just testing you guys right there. Okay, perfect. Let's see if we were right. False, false, true. Yeah, looks right, yeah? Yeah, okay. Perfect. Okay, let's do some multiple choice. A key feature of long-run equilibrium in a monopolistically competitive market is that what?
B.
It is B, yes. Price will equal to price will be more than marginal costs, but it will equal their average total cost, meaning they'll have zero profits. Yep, okay. In Bertrand, with two firms producing identical products and facing the same constant marginal cost, the Nash equilibrium is what?
Marshall point.
Yes, it's B.
B.
Right? Their firms, their price will be equal to their marginal cost. Okay. In this game, what is the pure strategy Nash equilibrium? Oh, actually, I'm going to skip this because we actually did this. This was the whip nene example. So, yeah, you can just read these in the video with your eyes. When you watch, you can watch them. Okay, 14. Forcing a natural monopoly to set its price equal to its marginal cost is
C.
C.
C. It will lead to the firm exiting the market in the long run. All right. A market has an inverse demand curve of P equals 200 minus Q, and all firms have a marginal cost of 0. Consider the total profit generated by the entire industry in these scenarios. What scenario would result in the highest total industry profit? A single price monopolist, a Corno duopoly, a Corno oligopoly with 10 firms, or a monopolist charging different prices to 2 submarkets with different elasticities of demand.
It is clever.
That was mean.
You think it's D?
I think it's
a guess.
D. Yeah.
You think it's D? Why D?
Because price discrimination rules.
All right, we'll take it. We'll take it. It is D.
Is it D?
Yes.
Because the other ones don't actually necessarily impact the ability of the market share versus the consumer surplus versus the producer surplus in that market. What actually does that is D, right? Because you're able to use some type of price discrimination. In this case, I believe it's price discrimination 2 or 3. It's 3, right?
Yeah, this is third degree.
Yeah, so using the third degree allows you to be able to capture more of that. And remember how all of these create deadweight loss except for D? D minimizes deadweight loss and therefore produces more efficiently and captures more market share.
And put really simply, if you have one firm, your total profits are going to be higher than if you have a bunch of competing firms. So what you want is a monopoly. That's going to give you the highest total industry profit. And then what you want is a price discriminating monopoly. Minimize competition, maximize discrimination.
Create my own company and rule the world.
Yeah. Okay, so a monopolist is practicing perfect price discrimination, which the following is true. Consumer surplus 0, producer surplus 0, inefficient outcome, or marginal revenue less than price.
Consumer surplus is 0.
Correct, consumer surplus is 0. Yes. Which the following does not follow from the Xiao circle model. Price is falling in the number of firms. Number of firms increases in travel costs. There are less firms than is socially optimal, and the number of firms decreases in fixed costs.
Thinking it's C, but I can't explain it.
It's more
Wasn't it more
firms.
firms than the social option?
Yeah, exactly. You get over differentiated, not under differentiated. The rest of these are true. Okay, perfect. And then we have some smarty questions as well. You guys will love this one.
I hate that.
You got a market with an inverse demand curve.
So bad.
Any and all firms in this market have homogeneous goods and a cost function of C equals 10Q. You'll find the long run P and Q in perfect competition for a monopoly, for cartel duopoly, for Corno duopoly, for Stackelberg duopoly, for Bertrand duopoly. The entry fee charged by a 2-part pricing monopolist, and assuming a market segment with a different demand curve, the price and quantity for a price discriminating monopolist.
I feel like you had a lot of fun when you made
Is
this.
that what it will look like? Because that
Yeah,
covers
like-
pretty much everything.
Like, is
That's why I put it there.
Question, like, because I know in the past you've been like, well, in the homeworks we get these like long multi-part questions, and you're like, okay, well, Dr. Lewis doesn't really like to structure his tests like that.
It's true.
So, is that kind of thing something that we might need to look?
I put this on here
Just so
because
we can practice everything.
I think you should know all of those.
Okay.
You can see an example for Corneau, Stackelberg, Bertrand, 2-part pricing.
But like, how might? I guess my question is like, how might he go about asking? Like, is there gonna be anything weird, or expert.
You would probably
have to be able to like.
You'd probably ask one of these. Like, you know, he might ask you to do Cournot, or he might ask you to do Bertrand, or he might ask you. Notice for this question, for part F. Why might part F be easy to do in this scenario?
Because you just swap the Q and the P, it's symmetrical.
Yeah, it's just goods. And so if the goods are uniform, then we can just assume that P is equal to marginal cost, so price is equal to 10.
Yeah. So you know that it's undifferentiated Bertrand in this case. Unlike question 20, which says that there are two firms competing with differentiated products. See, I gave you guys everything. Absolutely everything.
We love it.
So you can have a lot of fun with this. And then there is a game right here. And we covered games. We covered the discount factor. Yeah, I feel like we pretty much did this. Oh, we did this. Yeah, we did that. Okay. Cool. So that's it, guys. That's all I have. What questions or concerns do you guys have that are left?
Do we need to know there's a, I forget what it's called. Is it it starts with an R, but it looks like a swastika. That one graph where it talks about the different probabilities.
Reaction functions.
Reaction functions graph.
Yeah.
Is that something we're gonna have to know how to graph and make? We didn't really do it in class at all. I don't remember doing it in class at all. You remember? So she doesn't know.
I don't remember no swastika function.
If you look in I think it's like lecture notes for number 11. There's a reaction function
Yes.
graph that looks a little sus.
It is unlikely you'll be asked to draw swastika on your test.
I was going to say, I was like, no, thank you.
That would be awesome.
Yeah. How you guys feeling? Energized? Party.
I feel like it's doable.
I think there's just like little differences between all of them that when I'm solving it out, that will be really where I make mistakes. You know, so I just like maybe I gotta do a lot of examples of Cournot from Stackelberg to Bertrand.
Yes.
So just little differences in each of them and some of them go off of each other. Like the Stackelberg one, you can use the reaction function and then work backwards, like, you know. But
Mhm.
I gotta get familiar with using random letters and alphabet stuff.
Yep.
Like alphas and betas and whatnot. Gotta
Yeah.
get familiar with that. Can't use real numbers.
Really make sure you guys know how to do this stuff. Yeah, the difference between Cournot and Stackelberg and Bertrand. I mean, this is undifferentiated, but make sure you know how to do differentiated Bertrand. Make sure, judging by your guys' homework, make sure you know how to do mixed strategies without chat. Yes, that's all infinitely repeated games. Those are probably the most mathy parts of this. And you have Monopoly stuff, but like, pretty sure you guys all did that in 380. So I don't think third degree price discrimination is new to anybody here. Okay, so leave a like, subscribe, leave a comment down below. What do you think about Econ?
First link in bio. Steven.
Donate to my Patreon.
Yeah. Do you want to buy a Dogonomics t-shirt? Collecting demand. Okay.
One of his 4 subscribers.
Yeah. And it's 12 subscribers now.
We're at 12 now?
Yeah.
Shoot, I got in early.
Okay. Do this practice test. These smarty questions are good. Make sure you understand all these other concepts, and thanks for coming.
Excellent.
Awesome. Thanks, Stephen.
thank you, Steven.